All right. So whoever's listening to this, you might have missed this part, but we just went over this one. Now you can pause the video. Okay, and then we went over this one. Okay, and you can pause the video if you need to see it. Okay, and now we're moving on. All right. So homework. Any questions?
Yes.
Britt.
I would like to ask about question 39.
39.
39.
All right. Now, 39, I probably should have asked this entire section because a lot of people are confused on 39, and it's much easier than you're making it out to be. It has to do with this whole shifting and stretching and so forth. So back on page 95, is it? It's 96. There are 5 graphs. There's an F and a G and a K and an H and an L or whatever. There's those 5 graphs, okay? On 39, they wanted you to write the equation of the tangent line, which of course means we do this, right?
Yep.
Right? We need a point, we need a slope. Now they want the tangent line to F at 1. So you need F of 1 and you need F prime of 1. Correct? They want the tangent line at x equals 1. So we need those 2 things. Well, F prime of 1, they told us in the directions was 4. Right? And so all we need is F of 1. So we go back to page 96, and of those 5 graphs, which one is F? The top one is F. So all you have to do is look at that graph, go to 1, see the y value, and it's what? Isn't it about 5? Right? You see that, Brendan? You see it? No.
I don't see it because Dylan Graff borrowed my book, second block, and forgot his card.
There you go.
I'll share it.
Would you share? Okay.
It's not my fault, Mr. Clark.
I
It is.
totally believe you.
Shoot out Dylan on Monday.
Okay. So he took your book. Okay. So the F graph is the top graph on page 96.
Yep.
And F of 1 is 5. So all we have to do then is we put a 4 there, we put a 1 and a 5, and we got that. Now, that was really easy. Now, but there's a little more to this, so while we're on it, let's talk about this. So on 40, they wanted the tangent line equation of G at -1. So in that one, you would need G of -1, and you would need G prime of -1. So now look at the G graph, which is what? The top left one of that group of 4. And so what do you notice about the G graph? What do they tell you about the G graph? The G graph is, now don't look at the graph itself, look right underneath the graph. F of x plus 2, which means what? It's the F graph shifted 2 to the left. So if you took the F graph, which we just got done talking about what was happening on the F graph at 1, what will be happening to the G graph at -1? The same thing. Good job. It's the same thing, but shifted to the left too. So what's the slope of the G graph at -1? Because if you look at the G graph, you can't even see x equals -1. The slope of the G graph at -1 is 4, and the output would be 5, and so it would be that same answer in number 40. So I probably should have assigned a couple of those to make that connection. But what we were saying yesterday is when you shift these graphs around, but you don't change their slopes, then their slopes will be shifted, but they won't be changed. If you stretch a graph, then that changes the slopes. Okay, so we'll get into that and talk about that a little bit more today. But that's what was going on there. Okay, what else? $46. Okay? Now, 46 says that, what's it say? F of x is square root of x minus 3 all over x. All right? Now, what I would like to do before we do that one, I would like to write down some of the rules and maybe one rule that we did not write down yesterday. Now, of course, the big rule was the power rule. right? So the power rule says that if we have x raised to a power, then we bring the power down in front and we have this. Now this rule should be the most basic derivative rule we have, and it should be one of the easiest ones that we deal with. Now, you're going to get into fractions, you're going to get into negative powers, so you do have to deal with those. So maybe derivative sine is cosine, maybe it's easier. There's not much to do there. But one thing you have to be careful of is this rule just tells you how to handle x raised to a power. It doesn't really go beyond that. We really need other rules in conjunction with that. Now, I tried to get into some of that with the stretching and all that. So let's write down a few of those. Like one of them we talked about yesterday is this one. If I have a constant in front of a function, and I want to do its derivative. For example, 4x cubed. I have a 4 in front of x cubed. What do we say we do with that 4? It just hangs out there, right? We're going to bring the 3 down in front, but the 4 is going to still be a part of the problem. So the 4 will be there, we bring down the 3, and we do our normal power rule, and 4 times 3, of course, is 12. So what would the rule for that be? The rule would say, well, you just leave the k there, and then you do f prime of x. You just follow the rule for doing the derivative of f. Does that make sense? So if I have k, a constant, times a function, I just leave the k there, do the derivative of the function. That's what that's saying. Okay? All right. So here would be another rule that we had yesterday. We said that if you do one function plus another function, or minus another function, I'm running out of room here, I'll go to the next line. That derivative is what? Anybody have an idea what I would write here? F prime of x d prime of x. Didn't we say that yesterday? What we said is that if you had 3x squared minus 5x cubed, that's one function minus another function, that it's okay to just do their individual derivatives. Do the derivative of the first one plus or minus the derivative of the second one. So this answer would be what? 6x to the first. Now, that might not seem like a big deal, but that's actually a very big deal. That's the rule, because that's how we'd hope it would work. That makes sense that it works that way, but they don't all work that way. Okay, for example, let's do multiplication. If you had to guess, or if you had your way, what would be this derivative? Wouldn't that be nice if that was the derivative, right? It's not. It's not. Okay? In other words, we've learned these rules about what a derivative of a thing is, like x to a power, the derivative of sine is cosine. But we can't just go in a function that's got combinations of those things. We can't just go grab out the individual pieces and do their derivatives and think that's going to work. Now, I can show you a quick example of why this doesn't work. All right, example. Let me show you why the plus one does work. So let's say I had two functions added together. Okay, there's two functions added together, right? 3x squared plus 8x squared. Now, okay, that's f. Now, let's talk about the derivative. Well, according to this rule, we should be able to do each individual derivative, right? So what's 3x squared? 6x. And what's 8x squared? Now, I know you guys are looking at me like I'm crazy because what you wanted to do here was what? You wanted to add those together, didn't you? And that would make 11x squared. Now, what's its derivative? 22x. Now, didn't they both work out the same? They both work out. So that tells me, oh, okay, no problem. I know that this should be 22x because I know if I add those together, I get this. and the derivative of that's definitely that, so I know that's right. So evidently I can add them together, do their individual derivatives. That evidently works. Okay? However, if I come in here and do that multiplication thing, something similar, let's take 4x squared times 8x cubed, all right, and call that f. Now we know what should work. What should work is for us to go ahead and multiply those together, right? Which is what? We know that's 32x to the fifth. And we know according to the rules we do have so far that the derivative of this should be what? All right, a few of you got it. It had to be 160 x to the. We know that's what the derivative should be. I mean, we feel pretty confident about that, and we feel confident about that. Okay? But would it be okay to just do this derivative and that derivative and times those together? Well, let's try it. So do that derivative there. 8x. Do that derivative there. 24x squared. Now put those together. Does it equal that? It clearly does not equal that. So it did not work on a product to do their individual derivatives and then jam them together. So there must be some other thing we have to do, and there is. It's called the product rule, and we'll learn that later. Okay? And the same thing with a quotient. If we have a function divided by another function, unfortunately, we can't just do the derivative of the top thing, derivative of the bottom thing, and just do it. So for these rules to work, for these derivative rules to work, they have to be in a form that fits our rules. So we were a little rushed on that yesterday, so I didn't get a chance to really go through a lot of that. But, for example, 46 then is a good example. Oops, I got it back here. So here's 46. So, of course, I think most of you understood that you did need to write that as x to the 1/2 first, right? But what we can't do, even though we'd like to, we can't come in here and just do the derivative of that, the derivative of that, the derivative of that, and we just can't. It doesn't work. Okay? So we need to do what?
Split it.
Split it.
Can you rewrite it as x to the 1/2 minus 3 and then times x to the -1?
There's two different ways we can do it. One way, somebody said split it. Okay? So one way would be to do this. Right? Now that's a technique that we will use a lot in a later thing we do, so it'd be a good one to get used to when you have a single denominator. And I had some in the other class that rather thought of it this way. And they brought the x up top as x to the -1 like that, right? Everybody familiar with the negative power, right? Flips, right? That kind of thing. Either one of these is fine. Okay, on this one you would subtract the powers. 1/2 take away 1 would be -1/2. Here you would bring that x up to the top as 3x to the -1, correct? On this one you would distribute and add the powers. So -1 plus 1/2 would be x to the -1/2. And then this times this would be 3x to the -1. Either way you get the same thing. Okay? Either way you get the same thing. Okay? I think when you split it here you can almost get faster with it. You can just go 1/2 minus 1 or whatever. I don't really care, but either way you get to here. Now remember, we haven't done a thing with this yet except algebra. We're still on the f function, right? Now we're ready to do the derivative. So we bring the -1/2 down in front. That'd be x to the -3/2. We should get used to using improper fractions without a calculator. If you want to use your calculator, double check some of these, that's fine. Bring the -1 down here, be plus 3x to the -2, like that. Bring the -1 down in front, -3, that makes positive. Subtract 1 from your -1 makes -2. Okay, and there is your derivative. Okay, now, all right, what else? That, I mean, if you understood that now, then looking back, if you had questions on some of the other ones, you probably can see what you needed to do. I mean, you just need to do some rearranging. Now, there was one that came up in the other class. I think it's 35, 1 over x plus 4. Well, what you need to do is just move that. Think of this x plus 4 as first power. And so you just write the whole thing as x plus 4 to the -1. Right? Now, when you do the derivative, you can bring the -1 down in front, x plus 4 to the negative 2. Because again, what's that plus 4 do? Right? It's just a shift left, actually, right? It's a shift left. So all the slopes will shift to the left, but they won't change. So your derivative will still have the plus 4 in it. It'll still have the shift in it. But you'll just do your regular power. Okay? And then the same thing is true on 36. Was it 36? You had 3 over x plus, what was it, x plus 1 squared. You just bring that up with the 3, like that, negative 2. Then you bring the negative 2 down in front. Now to do your derivative, you bring the negative 2 down in front. Okay? All right, now there is one rule I did not discuss with you, and so we should write, let's rewrite a few of those. The one with the shifting, let's write that as a rule. You don't have to write it down. I don't care about that. But if you had f of, and then let's put an x plus k on the inside, so that's just your shift, left to right. Then the derivative of that is simply f prime of x plus k. Right? We just simply do the normal derivative we would do, but it'll still have that x plus k on the inside. I think this is on, these versions of these are on page like 95 or something, I believe. Okay? So we talked about that shifting thing. We talked about if you had a number on the outside. Oh wait, I did that one already, didn't I? Did I write? Oop. Right here. If you have a number on the outside, that number will just hang out there, right? So what I haven't talked about, from a rule standpoint would be this one. Two of them actually. What would happen if you had a vertical shift? What would happen if you had a vertical shift? Does that affect the slopes? Does that change where the slopes are? It doesn't really do anything. What would be the answer to that? Well, we did one of these problems yesterday. Let's do an example here. Let's do x cubed plus 7. What's the derivative of that? Plus 0, right? Now, we didn't talk about it yesterday as a vertical shift. We said we used the sum rule, which says you can do each of these derivatives individually, right? And that's fine too. So the derivative of that's 3x squared. Derivative of a constant is 0. But now that makes for kind of an interesting thing to think about here. So you're telling me that if I had x cubed minus 4, what's its derivative? You're telling me those two have the same exact derivative? We did kind of figure that out yesterday, but wouldn't that be because of a vertical shift, right? Those two graphs are just vertical shifts of one another. They have the same slopes at all the same places. Now, if you think about this, haven't we done this when we did graphs back in chapter 1? Remember when we would have an f prime graph to start? Pretend our f prime graph was this graph, 3x squared, and then we were going to draw the f graph. Where did we draw the f graph? Where did we start? But we didn't know, right? We could start it anywhere because there was a bunch of them. So if you have a single f prime, there could be an infinite number of f's that go with it, but they are all the same except for a vertical shift. So this kind of shows that. Same f prime, two different f's, but the only difference between them is the vertical shift. Okay, that's something we'll get into when we get into antiderivatives and we kind of go backwards with this stuff. Okay? All right, so that kind of makes sense. So here's the main one that we haven't talked about. This one's kind of tricky. What if you have a number multiplied on the inside? What if you have a number multiplied on the inside? Now, what does that do to the graph, first of all? Stretch or compress this way. If you compress a graph this way, what's it do to the slopes? So wouldn't it make them steeper if you compress it? And if you stretch it, it'd make them actually shallower? So if you let's do compress. If you compress, it's actually going to make them steeper by that amount. Does it change where they are? Horizontally. Does it change where they are horizontally? I think it would, wouldn't it? If you had a point on the graph that was over here at 4, if you compress it by a 2 factor, where is it now? At 2, right? It's half. So it not only changes where they are, but it changes what they are. We have 2 different changes. Now that's the only one where that happens. If you vertically stretch a graph, it makes them steeper, but they're at the same places. Okay? Horizontal. But if you compress a graph like this, it changes where those points are horizontally, and it changes their slope. We have 2 different changes going on. Now, if things were going to work out really nice for us, come on. Computer's getting a little bogged down. Okay, slow down. If we had the graph, let's pick an easy one that we can actually manipulate and tell. Let's 7's too good. Eraser's too big. Let's make that, we'll just make it square, because that'll make it easy. If our rules were going to work really nice here, kind of like they did with shifting and stuff, this derivative would be what? You careful. Yeah, you'd bring a 2 down in front, right? The 4x would stay the same to the first power, which of course we know would be 8x, right? But we could simplify this, couldn't we? What's 4x quantity squared? 16x squared, right? We know that's true. And what's a derivative of 16x squared? Our answer should have been 32x, not 8x. We were off by what? Were we off by a factor of 4? We were off by a factor of 4. Why was that? Well, we kept the 4x on the inside, which takes care of the fact that the slopes are now at new x locations, right? That takes care of that. But what we didn't do is the fact that if you squeeze that by a factor of 4, all those slopes are what? 4 times as steep. So we not only have to keep that 4 on the inside when we do this, we have to kick out a 4 to take care of the steeper slope. So the slopes moved in by a factor of 4 and got steeper by a factor of 4. We need to do both of those things. Do you see what I did? Okay. We need to kick out a 4. So the rule is this. If we have f with a constant multiplied on the inside, we can do the original derivative. We keep the kx in there, and we have to multiply by the k on the outside. We have to kick out that k because of it does 2 different things. It compresses and changes where the slopes are steeper and does it. Now, to be honest, when we get into this, you're not going to think every time, oh yeah, it compresses and every da da da. You're not going to remember that. You're just going to say, oh hey, when I got a number multiplied on the inside, I got to kick it out. Right? You're going to do it that way. So, for an example, another example. If we had 3x plus 1 to the 5th, what's that derivative going to be? Okay, first bring down the 5. The inside stays the same to the 4th. And then another 3 kicked out. Because that plus 1 is in there for this shift, but we don't care about that. I mean, we take care of that by just leaving our inside the same when we do our shift, or do our derivative. But that 3 that's being multiplied on the x there is going to cause a compression, so we got to kick out a 3. Now we should go ahead and simplify that a little bit. The 5 and the 3, put a 15 out in front, 3x plus 1 to the 4. Okay, now here's where the calculator can come in. So let's go ahead and get our calculators out. And hopefully you're all logged in. And here. Sam? You have your calculator? Sam's our presenter. See, he thought he would not log in and that'd get him out of being the presenter. Didn't he? somewhere. Happy Thanksgiving. All right. Logged in, Sam? Thank you. All right. All right. So, go to the calculator screen, and I want to show you where your calculator can, this is the CAS part of the calculator. The Computer Algebra System is what CAS stands for. The fact that we can solve algebra equations is part of CAS. A non-CAS calculator can't do that. If you go, Sam, next to the 9, there's that's called the template thing right there, okay? You'll find the derivative. I think I showed everybody this, but this one right here is the derivative template. And notice it's written much the way I've been writing my derivative formulas. So put an X down there in that bottom box. And then here, let's do a couple of tests. For example, just type in x cubed right now. Just do a real simple one. And hit enter. And look at that. Does a derivative for you. Pretty cool, right? So there will be times we'll use this. Now, not till later, like in chapter 4, when we're doing applications of derivatives. Most of the time, and we'll have a big test called the gateway test on derivatives, where it's all no calculator. So most of what you'll do is no calculator. But you can use this to check your answers when you're practicing your derivatives. Yes? Yes. Yes. Now that's actually in that template thing as well, the limit one and so forth. So yeah, a lot of these can be found through the menu as well. Okay? All right. So now let's go to, and do number 46. Now on 46, let's go ahead and go back and get your derivative again. Go grab that template of derivative, put in x, and let's put in number 46. So get a fraction, so we'd want a fraction there. And then it was what? Square root of x. And then make sure you arrow out of there. There you go. Minus 3. And then over x. And hit enter. Now, that doesn't look anything like the one we got for number 46, does it? So here's the dilemma. When you are working at home and you're practicing derivatives, no calculator, and you want to check and see if you're doing them right. So you can get your, and I call this calculator kind of electronic solutions manual, right? I mean, you can get on this thing and you can check and see. Well, you look at that, you look at your answer, and you're like, hey, those aren't even anything alike. Well, let's type in the answer we got. Now, sometimes it's as simple as that. So what did we have? We had negative 1/2, right? So let's type that in, negative 1/2. X to the, what was it, negative 3/2? X to the negative 3/2 plus 3x to the negative 2. Now sometimes, whatever you had gotten, if you just hit enter, the calculator will simplify it in a way that it'll look just like the other one. Now in this case it doesn't. So you're saying, oh geez, I got this. See, the calculator wanted to go back to positive exponents, so the calculator got this. When the calculator did the thing, it got that, and you're still looking at that saying, geez, I don't know if those are the same. Now, some college professors wouldn't let you use this thing, and they'd be making you do this all by hand and show that they're equal and all that. Yeah, a lot of algebra stuff. But, so there's a couple ways on your calculator you can do this. Not just to show, just so I can show you a couple things your calculator has. Like, for example, that answer we just got, that bottom one there, is 2 fractions subtracted. The calculator will get a common denominator and put those together into 1 fraction for you. So if you go up to your menu, go ahead and hit menu, and go to algebra, and then go to fraction tools, and common denominator. And then, now your cursor's in the middle of the parentheses there. Now arrow up to that answer we just got, hit enter. And now what that should do, oops, There you go. Hit enter. That should take those two fractions, get a common denominator, and put them together. Now, it doesn't quite look, if you arrow up to that other one, it doesn't quite look like that one, but you can tell it's the same. It's just got a negative factored out of the top is all. Okay? Now, somebody in the other class, I think it was Quentin, saw something that was kind of cool, that actually worked a little quicker than doing that. Right now, Sam, type in 3 equals 3. And it says true. Type in 3 equals 4. It says untrue. Okay, it says false. Okay. Now, so arrow back up, up one more. Okay, so here's what you could have done. You could have said, all right, here's what they got, and here's what I got. So we could have said, go ahead and hit enter. Okay, so we could have grabbed what they got, and then hit equals, and then go up and arrow up and grab what we had, which was that. Hit enter. Oops. Oh. Yeah, delete that time sign there. There you go. And so, whoops. Yeah, it's got to go before the negative one after. You can't change it there. You got to hit there. You go. He's purpose, kind of like I do at home with laundry. He's purposely screwing it up so he won't have to do it anymore. Get rid of that time. Okay, it says true. So that tells you that those two things are equal. Okay? All right. So that, anyway, that's something you can do when you're working these problems. Now, here's what I wanted to use this for. So now we can see this thing that we just got done talking about a minute ago is actually true. We can use the calculator to kind of verify some of this for us. So let's do this 3x plus 1 to the 5th. So Sam, go ahead. You're not done yet. 3x, let's do that derivative. Grab that derivative template again. And do the quantity. You need another parenthesis. You'll need another left parenthesis. 3x plus 1, and then that's all to the 5th. Hit enter. And sure enough, we did need to kick out that 3 to get the right answer there. All right, and now do this one. While he's typing it, what would sine of 2x, with the 2x on the inside, what would sine of 2x, what would you expect that to be? The derivative. Put a 2x in there. Don't hit enter yet. What would we expect that to be? Cosine 2x with a 2 kicked out, right? So 2, go ahead and hit enter. And sure enough, there it is, 2 cosine 2x. So when we have that number multiplied on the inside, that compresses the graph, so it makes sense that we'd have to kick that out to make those slopes twice as big. Okay, so with those, just a few basic rules and an understanding of if we put constants in there, or we add constants, or we have some on the inside or the outside, how that affects it, we can do a pretty wide variety of functions. We can find their derivative equation, okay? And so using this shortcut. And again, it all does still stem back from the definition of the derivative. All right, so that's the first thing I wanted to do was go over the homework, just talk about some of those rules. If we get some time at the end, we'll see. I've got a website. Well, I could show you that website. And now I want to look at the other thing we're doing. So on our class website here, I've got a couple of videos here. Now I've got one link I've put here says helpful class videos. Now I just found this website, AP Calculus Stillwater. This is some other class, and got a whole bunch of videos on various things, like basic derivatives using the power rule, for example. Okay, and it's just like mine. It's kind of a YouTube video, but he's not nearly as exciting as I am. But the nice thing about his is they're very specific to specific things, and they're only, like this one's 14 minutes long, instead of like an hour. Instead of like an hour like mine.
How many views do you get?
And he's got 590 views. I get like 8. You know, I mean, well, just how many people are gone. Although, this is kind of interesting. I did get, I have gotten a few comments. Mine are public, but the name of my video is November 16th class video. So who would search, you know, I mean, it would be hard to find. I'm not sure. But I do have a couple of videos out there that I named with calculus type thing. And I have gotten some comments, some people on there comment, hey, thanks for the video and help me study for my college test or something. It's kind of cool. So yeah, I think I'm up there. I've got one video that's got like 30 views or something. So I'm big shot. Yeah. All right. So anyway, I need to figure out a way to make some money on this and quit this gig. All right. Anyway, so I've got a couple here. Derivative practice 1, derivative practice 2 are ones that I've found. Now every year I try to find some of these, and then the next year they're shut down or the link doesn't work anymore. But here's one from Bluffton University. Bluffton. I have no idea. But it's kind of cool because you can pick your level. 1, 2, 3, 4, and quite nasty. You can choose which different trig functions in e to the x you want. Okay. Now, well, hang on here a second. So it'll include polynomials, which are the ones we're talking about, and root functions like square roots and stuff. So it'll include those, and it'll include some other ones if you want. So if we do a level 2, and I uncheck all those boxes, and I hit start over, okay, so here's 8 times the 6th root of x plus x to the 5th. So here we can type in our answer, and we can submit our answer, and it'll tell us if we got it right. Okay, and we hit start over, it'll give us a new one. Yeah, let's look at it. So anyway, and then you can play around with these. So quite nasty would be the square root of the square root of. Now, if you would include like some of these other functions, you know, like logs and
every single one.
now it won't actually include them all in every problem, but you know.
People just sit in an office and
Well, evidently, they've made up a database of these problems. So anyway, this is one website where you could look at some of those things, and then this one is just at this test they've got this some practice tests and they've got solutions. Like so, this just pulls up a PDF. If you do practice test 1, now this is from 2003, so I don't know how much longer this website will be around. But okay, so at this college, they had let's see, I'm not sure how many's on here. There's about 20, and then a bonus. Now, at some point, we'll be able to do all the ones on here. Right now, we would be restricted to, well, we should be able to do number 1. Be able to do number 2, number 3, number 4, not number 5. You really can't simplify number 5. That'd be a quotient rule kind of thing. We could simplify this one. We can't simplify this one. You see the difference between 6 and 7? You have a single denominator here, so you could split this apart. This one you could not split apart. There would be no way we could simplify this one algebraically. 8 we should be able to do. So there'd be a handful in here that would be just power rule. So anyway, as we get closer to doing our test over these derivatives and stuff, we'll talk more about those. So anyway, I've got some of those on there. All right, let's shift gears here a little bit. And everybody stand up and let's take a 45-second break. Okay, stretch a little bit, do a jumping jack or two. Whatever. Whatever it takes. No, I had a college class once we did that. An hour and 15 minutes. We'd all do jumping jack. We'd all do jumping jack.
Those stretch breaks were the greatest thing.
Especially after lunch, you know.
Stretch breaks. God, if we didn't have those, I would have literally died.
Just for that problem.
In AP American history, we get like 10 minutes.
Yeah, I'm not a believer, no. As a matter of fact, there is actual brain research that says about a 45-second break, a 10-minute break, then you lose everything you've been doing, and then you gotta restart. All right, everybody sit down. Time's up. Oh, shoot.
You need like 3 or 4 sheets of paper just to write it down.
And then I'd like that's what I'm saying.
All right. We were just talking up here about how, what was it, history or something? You get like 10-minute breaks, well, yeah. There's actual research that shows a 30-second minute break is good for the brain to get right back at it. 10-minute break, not so much. They pretty much got to restart. Yeah, power nap. Well, power nap, yeah. That'd be good for your overall health, I think, probably, but not to get right back on top. So anyway. Yeah, probably true. Probably true. You guys can help remind me if you start falling asleep like this. If you think we need a break, start closing your eyes.
How about a minute?
Every 10 minutes, a minute break. I don't know. All right. So let's go back to yesterday's assignment, number 34. Okay, and on number 34, the part we did yesterday is we said, hey, this derivative here looks special, or this limit problem looks special. It looks like our definition of a derivative with the a plus h and all that stuff, right? And we said, so what is this? What's going on here? So what did we say? That this limit was representing what function? Remember what it was? It was the square root. No. It was the square root of x.
Plus
And it was at the point, so what it was doing was finding the derivative of the square root of x function at 9. Okay, now let's review that real quick. I want to make sure everybody's okay with that. So if we go back to, because that's the first part, and that's the part from yesterday. So if we go back to this problem right here, f of x plus h minus f of x all over h, when we see, well, matter of fact, we should go back even farther because now we're doing a derivative at a specific point. So we should go back to this problem right here, and we should look for, see what we're doing when we write number 34, we're doing this problem right here. We're looking at this and we're saying, hey, what function must this have been? Well, the key is right here. What does f of 3 plus h mean? It means take 3 plus h and do what? Put it in where the x was. Now, let me say that again. This is critically important. F of 3 plus h, which is the first part of our definition, says take 3 plus h and put it where the x was or is. Well, if we're going to work this backwards, then that piece of information is vital. When I look at this, I'm going to focus on the 3 plus h. Because I know that that was a very important part of this definition. I see the 3 plus h, and that says to me, hey, that's where the x was. So when I see a 3 plus h there, I think there was an x there. And I see a 3 plus h there, there was an x there. What was my function? X squared minus x. And so that tells me my function must have been x squared minus x that created this. And because the 3 in the 3 plus h is where I'm doing the derivative at, that 3 has a special meaning as well. So when we come over here now to this problem that we have on the board, all right, then that tells me that this 9 plus h, we use delta x here instead of h, same thing, this 9 plus h must have been where the x was. So this function was square root of x. And then, of course, that 9 is where we were doing the derivative at. So this thing right here represents the slope of square root of x at 9. Now here's what the square root of graph looks like. We talked about this yesterday. And at 9, it's not going to be very steep. So we would expect to get a fairly small number out of this answer, right? Now, here's how we're going to do this. So the next question is, how can we actually work this to find out what it is? Well, one way to work it would be to do the whole long way with algebra. And we've already done that. This would actually be a great one to do conjugate on. If I was actually going to work, see, it's going to get confusing today possibly if you, I'm going to really try to make connections between what we're doing here and what we have done in the past. It's just another way, we're just looking at this in another way. It's not some whole new thing. It's just another way of looking at the same thing we've been doing. So one thing we could do with this is we could work it out algebraically. So we would multiply by a conjugate. This would be a conjugate one. What would be the conjugate here? Root 9 plus delta x plus 3. And I could do that up here and do that up here. And then I would FOIL and stuff would drop out and delta x's would cancel or h's would cancel, right? And I could plug a 0 in for h and we would get something. Okay? And that would be our answer. And it turns out we get 1/6. So if we did that the whole algebra way, like the one we just had up here a second ago, we would get 1/6. Now does 1/6 seem reasonable for that slope? Seems pretty reasonable. Pretty flat, positive. Seems reasonable. What I want to do today is use our calculator to get that same 1/6 answer. But just use our calculator to get it. Because what that's going to do is help us think about it in different ways. Now, to start with, we'll let Sam do this again for us. I'm going to give you the cheating way, which I don't think adds anything to our knowledge of what limits are. I think it just any trained animal or my 8th grade daughter, sometimes one and the same, but she could do it if I just, led her through the steps. It doesn't take a lot of thought here. But go to your template. So you can do this and use it. It's kind of cool and neat to see, but it's not really anything that's going to be of value to you, I don't think. And grab the limit. Grab the limit right here. That'd be hard for a trained animal to run the calculator. All right. And so see, we got this limit thing. Now I'm going to show you this, but we hardly ever use it. Because again, it's just punching buttons, and to me, that's not going to be a deal. So now delta x, we don't have a delta x key, so let's use h. Let's use h. So put an h in there, and then 0, and then forget that box. We don't need anything in that right now. And then let's put this fraction in there. Okay, so we got square root 9 plus h, then go out of the square root, minus 3, all over h, hit enter, and we get 1/6. Now, again, I don't think that did anything for your understanding of limit or slope or anything. You just typed in what you saw. Okay? All right, so that's that. But here's what I want to do. I want to do this where I try to get, and then this is what we'll spend a lot of time next week doing, is try to get you to understand what limits are all about. And I want you to understand their connection to slope and everything, but I want to focus on just this thing in the box up here for right now. So when we say find this limit, and we'll pretend this is an h here for right now. When we say find this limit, what we're saying is this fraction has some values depending on what h is. What I care about is what are its values, its outputs. What are these outputs of this fraction as its inputs, the h values, get close to 0? Let me say that again. What are the outputs of this fraction as its inputs get close to 0? Now, it turns out these outputs are getting close to what? No. 1/6. 1/6, right? These outputs, it turns out, are getting close to 1/6 when its input, h, is getting close to 0. And that 1/6 represents what? The slope of this graph at 9. So there's a lot of stuff going on. And we've really got two different functions we're kind of talking about. We're talking about the function square root of x and its slope at 9. But what I'd like to do is kind of forget that part for a minute and just focus on this. And just treat this red thing here as kind of its own function that has outputs as this input h is getting close to 0. So I don't want you to mix up this input getting close to 0 with this input being 9. Those are two different inputs in two different functions. Okay? So that's important to understand. All right. So just focus on this. So how can I look at a function's outputs and inputs? How about a graph? Well, we got a graphing calculator, so let's do that. So what I'd like you to do, Sam, is go onto your graph screen now. And, oh, that's cool. Yeah. I hope you weren't doing that during calc class. Okay. So, what class? Yeah. Oh,
I thought you were
okay. So anyway, and you know, and I don't think your chemistry teachers are dumb by any means. I mean, it's chemistry. But I mean, there are times I gotta admit where I'm sitting out here and we're working on something, and it doesn't have anything to do with a calculator at all. And I'm looking at some of you back there, and you're going, it is calculator. You know, hey, they're on their calculator. They must think that I'm thinking, hey, I got my calculator. I must be doing calculus. Like I said, how's the old saying? I was born on a Friday, but not last Friday. Okay. Anyway, so let's put. So what we want to do is put this right here in as our function. Okay. So now we called this delta x, and then we said let's don't call it delta x. Let's call it h. Well, now if I'm going to put this fraction, not the limit now, but just this fraction, if I want to put this fraction in, what do I have to use here? I actually have to use x now, so that even adds to the confusion. We had delta x, then we had h, now we're having x, okay? So we got to put an x there, okay? So did he get it in right? That's not a minus. That's going to be a plus there, okay? Okay, so now what we're going to do is we're actually going to graph it. Yes?
I accidentally figured this out when I was trying to do this problem.
Accidentally figured it out. That's what. Yeah. Go ahead. Yeah.
Just like putting it in and figuring out that that's the limit.
And as you were just, and then traced around. Yes, yes. And that's exactly what I see. Now it looks kind of like a, you know, we got all this empty white space. We could reset our window, but I don't really care what it looks like, right? I mean, what do I care about here? What am I looking for? No. See, now that's where I don't want to get confused. I'm not looking at this at all. This is our input right here, this delta x, which of course is now our x, right? No.
How about you decide what we do?
No. I heard it. As x is approaching 0, see this delta x, which was an h and is now an x, okay? We want it as this x is approaching 0, which is where on the graph when x is approaching 0? The y-axis, right? So we're interested in right there, right? When x is approaching 0, we're interested in what these outputs are, these y values, right? So we can trace. So go ahead and hit trace, and trace at 0. Type in a 0. Oh. Why is it undefined? Oh, isn't that the same thing we were doing when we were doing the algebra? We couldn't plug in a 0 right away then either, could we? We had to do the algebra and cancel and get the h's canceled, then we could plug in a 0. Okay, but I don't want to do the algebra. I'm not going to do all that. So I can't plug in a 0, so what could I do? Let's get something really close to 0, because that's all I care about is when this gets close to 0. So let's go trace again, and let's put like 0.0001. Hit enter. 0.16 repeating. What do you suppose that is? Okay? Now, okay? Let me catch my breath. I'm a little overexcited here. Now, on our next test, on the calculator part, I am going to ask, you will have some limit problems where you'll have to find a limit using your calculator. You cannot do what we did on the calculator screen and just do the limit and write down that answer. You'll have to justify somehow why you got what you got. Now, the easiest way to do that is going to be what I'm going to show you next. I mean, it's hard to show a graph and trace and how you did that unless we could take a screenshot and somehow transfer it to our paper or something, or you could email it to me. I mean, we're not quite there yet with the calculator. Can't email yet. But anyway, but I want you to understand this concept on a limit. Now, again, then I also want you to take it one step further and realize that that 1/6 that we just found here has a double meaning. It's not only the value of this limit, but it is also the slope of this graph at 9. So see, but they're like two separate things. Okay, so I want to do this. I want to go to the table, because the table shows these values. So hit Control T. Control T. And it brings up a split screen with the table of values. Now, arrow up, because I want to put the 0 right in the middle of my table. Just arrow up twice, right there, stop right there. And I want the 0 to be in the middle of my table. Now again, the 0, when x is 0, we know it was undefined, because you can't divide by 0, right? So we know it. So we want to get close. Now, these values on either side then, we can see are getting close to like 1/6, that's 0.1 something, but we want to be accurate to 3 decimal places, right? So what we need to do is we need these values to be like Sam said, 0.001 or something like that. So we go ahead and hit Menu. While your table is highlighted here, go and hit Menu and then Table. And then Edit Table Settings. Now, we want to always start our table in these problems anyway at 0, because we're talking about when x is 0 here, h, which is now our x. And then that's our step, we want it to be what? 0.0001, let's do 3 zeros. Because we want to get really close to 0. Hit Enter. And then arrow up a couple so the 0 is right in the middle of the table. Because I want to see on both sides, I want to see what it's approaching. And sure enough, 0.1666, so I could get accurate to 3 decimal places. So clearly, and that is 1/6, so we get that value. Okay? Yes. Oh, is that it? Okay. So, feels like there should be more of that. You guys are just so good. We go much faster than the other class. I don't know. All right. So you guys are going to get this done. Yeah, he slows us down. We gotta repeat it. Yes. Yes. I was just gonna tell you that. So now, here is your homework, which you should be able to get done quite easily here. Because once we have the table set up on our calculator and stuff. So John has asked a question, so on our quiz, where I say, find this limit. Matter of fact, I might not even say find the limit. I may actually tell you what the limit is, because it's right there in the calculator. And just say justify that this is the limit. And the justification, I think the easiest justification to give is that table. So let's look at number 1. So every one of these is set up so it should look like a derivative definition. So number 1 says, let's do this. Yeah, no, I know what it says. I'm sorry. I'm just thinking how I do this. Okay, so all right. So this first one here. All right. So f. So that this looks like our special definition of a derivative. And what function must it have been that set this up? Okay, yeah, I'm hearing all kinds of things, none with much conviction. Isn't it that?
Oh, yeah.
Right? Because what do we look at? We look at the 3 plus h. And the 3 plus h got plugged in where the x must have been. So right there, and this 8 is really what in disguise? Is really 2 to the 3rd. So here we had f of a plus h minus f of a, right, all over h. All right, and then and then this derivative, so this is really then, this whole limit is really the derivative of that function at 3. Yeah. Isn't it the a plus h? It's the a value is where we're doing the derivative. So it's really 3. Now, here's where this gets confusing because people a lot of times put 0. They'll say it's the derivative at 0. No. What does the h approaching 0 mean? The 2 points become 1, right? Our definition of derivative is always right, as h approaches 0. But that's not this input. This input comes from that. So again, keep those separate. So then the next thing I want you to do, it says use your calculator to estimate this value. So in other words, I want you to graph that and see what its values are as its input. H is getting close to 0. But when we put it on the graph, we have to call that x. So understand the difference between that 0 and that 3 and what they're meaning. So back on your calculator screen, okay, we're going to go into F1. And the beauty of this is now that your table is there and set up, it's really as easy as just putting in the new function and away you go, except now his table's gone. But that's okay. Hit Control T and it'll come back. Okay, now your setup's different. You're going to have to go back to your table settings, but that's okay. So just what you have to do is you have to click over here. You have to click over here on your graph to get it highlighted. Now hit Tab, and you can get into F1. Okay, and now let's type in that function, which would be, what was it, 2 to the 3 plus x, and then minus 8 all over x. Those x's are really h's though, okay, right? And then here we go. And of course we can't tell anything here because we're not zoomed in enough, are we? We need to be like 0.01, so go to your menu. Or you're going to have to click on your table. Yeah, I think you have to click on your table, there you go. And then go to your table settings. Table settings, it's kind of like you got Thanksgiving. Table settings, and 0.001, and then arrow up a little bit. So now, back to John's question. So on the quiz, to justify it, and now can't we see what this answer is? What would it be? 5.545, I think, rounded, wouldn't it? So it looks like it'd be 5.545 to 3 decimal places. Now, that number is what again? What does that represent? Slope of this function at 3. What's 2 to the x look like before you have a chance to disappoint me? I'll just tell you. 2 to the x isn't like e to the x, right? It's like e to the x. And at 3, right? Doesn't make sense to be fairly steep, probably. So 5.545, so that seems reasonable. But I would want to see over here, I would want to see a copy of your table. Negative 0.002, negative 0.001, 0, 0, 01, 002, and then it was 5 point, I don't know, what was it, 54496 or something, and 5.54499, and this was undefined, didn't have anything in it, and this was 5.545, oh, I don't know, something. And so I would want to see a copy of that table. And that is your justification. That to me would show that you kind of understand, hey, as the x or the h there gets close to 0, the limit is getting close to this. But it's also important to understand that has a second meaning, that it is that slope there. So on this worksheet, we're not going to hand this in. Okay, I mean, this is for you to do, and understand there will be some questions like this on the next quiz where you have to justify a limit. So put the table, don't put the table right now. That depends how lazy you want to be. You know, I mean, but you will have to do that. You just copy it right off the calculator, right onto your paper. Okay? All right, so go ahead and work the rest of the worksheet. That is your homework. You should be able to get that done. Just those 6 problems, that's it. That's your whole assignment. So go ahead and use your calculator, find those things, do the table. I'd like you to keep going through, doing the table, looking off the table, whether you copy down or not, it's up to you. Yeah, so every one of these problems on the worksheet, guys, I for sure I want to have this. Okay? For every one of the problems, I want you to have this for sure. F of x equals whatever the function is. And f prime of blank. And then what it equals. And I want you to do it on your calculator with the table. I want you to, but now you're already in there, right? So you just keep changing your F1 each time to that. Do it. Look at the table because you really need that practice. You need that practice of seeing the table, seeing what the values are showing you. And then, but whether you actually write down the table now, I don't care. But on the quiz, it will say justify that limit by using a table or a graph or whatever. And I would say a table is the best way to go. And then you will have to write that table. Okay? All right.